Okay, here is our second practice problem, Euclidean geometry, grade 11. Here we've got an 8.2 that says in the diagram below, ADF is a tangent to the circle with points E, B, C, and D on the circumference of the circle. Firstly, let us notice our tangent. So here is the tangent line, AD, which they mention. And you guys, the minute they mention that you have a tangent, immediately you need to think of tan chord. So think of your tangent theorems. The most commonly tested theorem with the tangent in grade 11 is tan chord. So we've got points E, B, C, and D on the circumference. Here we have it, E, B, C, and D. And what we notice from those points is that it forms a quadrilateral, which is cyclic. So seeing that EBCD is a cyclic quadrilateral, we know that we can apply the two theorems. Opposite angles of a cyclic quad are supplementary, and the exterior angle of a cyclic quad is equal to the interior opposite. So this is what you actually should be doing. As you read the given information, there should be certain keywords that the minute you read them, immediately you remember the theorems associated with those words. Then we're also told that AB is parallel to DC. Here you notice it by those symbols. EB and DC are parallel to each other. And also we are given that line EC and DC are equal to each other. So since we see that those two lines are equal to each other, what we realize is that this is an isosceles triangle. So we've got more than enough information given in order for us to answer the questions. The first question we have says, if CDF is equal to X. So they mention angle CDF as X. Let's find that first. Following on the diagram CDF, that's actually given to us. Here we have it. CDF as X. Name with reasons 5 other angles equal to X. Now this is a good 10-mark question. You need to give them 5 angles, which would be 5 marks, and their accompanying reasons would be the other 5 marks. So here's what we have to start off with. And what do you guys notice about angle CDF? Firstly, angle CDF is an angle between the tangent and the chord CD. So immediately we think of tan chord. If we follow the chord, we notice that the chord CD subtends an angle at E2. So this is how tan chord theorem works. The angle between a tangent and a chord at its point of contact is equal to the angle subtended by the chord on the circumference of the circle, meaning that angle CDF and angle E2 are equal to each other because of the tan chord theorem. So we have angle E2 equal to X. Okay, let's write that down as our first answer. Angle E2 is equal to X. That is because of the tan chord theorem. Next, now that we know that angle E2 is equal to X, angle D2 should also be equal to X. But let me show you why. We know that these two lines are equal in length, EC and DC. And we have triangle ECD, which now becomes an isosceles triangle. 2 sides equal, 2 angles equal. So because of this being an isosceles triangle, angle D2 would also be equal to X. So we would say angle D2 is equal to X, and your reason is equal angles, opposite, equal sides. Next, we're going to focus on the parallel lines. And I need you guys to notice that these parallel lines extend from A all the way to E, all the way to B. Second parallel line is DC. Then we've got this line A through D to F. And you're going to notice that what you have here is the F shape, which is corresponding angles. So angle D and angle A are both equal to X because of corresponding angles. Now to get the next angle, we can make use of the parallel lines again. And what I need you guys to notice, if I just highlight those parallel lines, we have an N or Z shape that forms. So if you have a look at this, from A to E to D, all the way to C, there is the N or the Z shape, which actually makes angle E1 equal to D2 because of alternate angles. So angle E1 is also equal to X. And our reason for that would be alternate angles. So we needed to get 5. We've got 4 out of those 5. Let's analyze our diagram to get the remaining angle. Okay, lastly, here's something that you need to notice. Now that we have angle E1, we realize that angle E1 is the exterior angle of the cyclic quad. Here we have the cyclic quad BCDE. And since E1 is the exterior angle, we know that it's equal to the interior opposite angle. So if we take C1 and C2 together, they are equal to angle E1. But we won't write it as C1 plus C2. Let's give it a proper name. We can call this angle BCD. So we now say angle BCD is equal to X, and our reason was exterior angle of a cyclic quad. But remember, it was angle E1 that was the exterior angle. But this is the theorem that we used to get it, okay? So it doesn't necessarily mean that BCD is the exterior angle. It just means that this is the theorem that was used to get BCD being equal to X. So that's often something that learners confuse. The theorem that you use to get your answer, that is what you write as your reason. Okay, so we have managed to find all 5 angles. Now, at point 2.2, we need to prove that ABCD is a parallelogram. Okay, so here is the quadrilateral ABCD, and remember, they want you to prove that it is a parallelogram. Now, there are many properties of a parallelogram that you had learned last year in grade 10 when you were introduced to quadrilaterals. But I want to focus on one of the more basic properties of a parallelogram, which says that the opposite angles are equal. Now, we can already see one pair of them that are equal. We can see that angle A and this part, which we called BCD, is equal to each other. So here's the thing. If we are able to prove that angle B and this D1 and D2 together are equal to each other, then we have shown that yes, it is a parallelogram because the opposite angles are equal. So my aim here is we need to figure out what angle B is. We also need to figure out what angle D1 is. So here's what we can do. I'll start off by getting angle D1. And this is how I'm going to do this. I noticed that angle D1, sorry. Let's have it like this. Line D is made up of D1, D2, and X. So we can easily calculate angle D1 using angles on a straight line. So what we notice here is that if we take 180 minus x again, we get angle D1. Angle D1 is actually equal to 180 minus 2x. Let's write that down. This is 8.2.2. Angle D1 is 180 minus 2x, and I got that by using angles on a straight line. Okay, let's fill that in on this diagram. D1 here is 180 minus 2x. Then, collectively, since I know what D1 is, I can get D1 plus D2. I'm going to call that ADC. So let's write this down. Angle ADC is 180 minus 2x plus x. Remember, this is D1, that's D2. Simplifying, I get 180 minus x. Okay, so what this tells you is that ADC, which is collectively this angle, that angle is 180 minus x. So for the sake of doing this question, I'm going to write that down. Okay, the color is not the best. Let's choose something that we can actually see. D1 and D2, that is 180 minus x. Now, our aim, remember, our aim here is to show that angle B is also 180 minus x. And what did we know? We had this on our diagram. I had erased it. We know that D2 is x. So I'm going to use D2 to get angle B. Because what we know is that this shape, BCDE, is a cyclic quadrilateral. We know that opposite angles of a cyclic quad are supplementary. So if you take angle B and angle D2, they should add up to 180. Seeing that we have D2, we can say 180 minus x to get angle B. So angle B is actually 180 minus x. Let's write that down. And we got that from opposite angles of a cyclic quad. So we've kind of already proved that this is a parallelogram, because what we've proven is that the opposite angles are equal. You've got 180 minus x, 180 minus x. Here we've got x and x. So we've proven that ABCD is a parallelogram. Now we're going to conclude, and we're going to say that angle ADC is equal to angle B, and angle A is equal to, we're going to call this BCD, which was x. Well, I mean, if you want to show what they equal to, you can. So if I just move this up a bit, I can say that ADC and B was 180 minus x to show that, okay, they're both equal to 180 minus x. And then angle A and angle BCD was x. Therefore, ABCD is a parallelogram. And the property that we used is that opposite angles of a parallelogram are equal. So even though you are in grade 11 doing grade 11 Euclidean geometry, they can still test you on theorems that you learned last year. So it's important to make sure that you revise through properties of quadrilaterals from grade 10, as well as learn your grade 11 theorems. Okay, so here we have it. We have proven that this is a parallelogram. Please remember to like, subscribe, and turn on your notifications for more content.